In the second part of this video, we will talk about limits that are. We'll talk about technique of evaluating these limits. There is something new for us, at least. And let's start with the first example. Here I have a limit of 2xy divided by 3x squared plus y squared as x and y are going to 0 as we're approaching the origin. So obviously the denominator is 0 for x and y equals 0, so this function is not defined at the origin. And as we can see, none of the techniques previously mentioned in the first video will not apply, right? I cannot factor anything in the denominator so that I can cancel with the numerator. And none of the identities are applicable here. So what are we going to do? Okay, so we're approaching the origin, right? And we can approach this origin along any path. So what will happen if we are approaching the origin along the x-axis? Okay. Okay, along the x-axis, y is equal to 0, right? So how the function f of xy is going to look, right? So f of xy is equal to 2xy over 3x squared plus y squared. So along the x-axis, y is equal to 0. So the function for all the points on the x-axis, the function f of xy will take the form f of x0. And now if you plug y is equal to 0, you get 2x times 0 over 3x squared plus 0 squared, or 0 over 3x. So now this, which is only 0, right? Now this limit here just becomes, because we are taking y is fixed, y is 0, this limit just becomes x is equal to 0 of what? Of 0 over 3x squared, which is 0. So I get that this limit, as I'm approaching along the x-axis for all the values on this line, this limit is 0. Does this tell us anything about this limit? Well, no, not necessarily. For example, what if we take y? What if we approach along the y-axis? Well, along the y-axis, now x is equal to 0, so f of 0y is again going to be 0 over y squared, which is 0. So this limit becomes 0 again. But is that enough to conclude that that the limit is actually going to be 0? What if we approach along the line x is equal to y? Right? I can approach the origin along this line right here. Well, let's see what is going to happen along the line x is equal to y, right? In that case, our function can be written as f of x. Instead of y, I put x, and then I get 2x squared over 3x squared plus, so basically what happens here, instead of y, I put x, right? So f of x is 2x, let's go step by step, times x. Instead of y, I put x, and here in the denominator also, instead of y, I put x. So I get 2x squared over 3x squared plus x squared is 4x squared. Okay, but now I cancel these two and I get 2 over 4, which is 1/2. Okay, so now the limit as x goes to 0, and if x goes to 0 along this line, right, y goes also to 0, of 1/2 is simply 1/2. And what do we know? That the limit doesn't exist if we have two different values for this limit. The limit has to be unique. So our conclusion is that the limit does not exist. Okay, So again, if this limit here exists, it has to be the same value as we're approaching this point along any path, along any curve crossing through that point. Okay, and here we saw that as we approach along the x-axis is the same limit as along the y-axis, but that's not enough to conclude that that limit is 0. Why? Because if I approach along the line x is equal to y, then I get a limit being 1/2, which is different from 0, and in that case we conclude that the limit does not exist. Okay, so we have a similar problem here. F of xy minus y is divided by x minus 1 squared plus y squared. Now x approaches to 1 and y approaches to 0. Okay, so basically we're talking about the point 1, 0, this point right here. Okay, we can take x is equal to 1, right? We can approach this line, we can approach this point along this line right here. Okay, in that case f of 1y is going to be equal, so x is 1, so y minus y over 1 minus 1 is 0, 0 squared plus y squared, y minus y is 0, I get 0 over y squared, and that's simply 0. So the limit of f of 1y as y approaches to 0, right? So I'm approaching this point by diminishing y towards its 0 value, right? So that's the limit as y goes to 0 of the constant 0. We've simplified that. That's simply equal to 0. Okay? We can approach this point along the x-axis. So take y is equal to 0 along the x-axis. Y is equal to 0. So if we take y is equal to 0, f of x, now we take constant y is equal to 0, we get x times 0 is 0, minus 0 is 0, over x minus 1 squared. That's also 0. So the limit of f of x 0, now send x to 0, is equal to the limit of 0, and that's equal to 0. Okay, now let us take, we can take the line, we can take this curve right here. Okay, y is equal to x minus 1 squared, right? The line x is equal to, y is equal to x minus y squared also passes through the point 1, 0, right? So then f of x minus 1 squared becomes what? X times x minus 1 squared minus x minus 1 squared over x minus 1 squared plus x minus 1 squared for y, right? And that's squared. Here we can factor out x minus 1 squared, so x minus 1 squared, and we're left with x minus 1 over x minus 1 squared plus x minus 1 to the power of 4. Okay, so we can continue simplifying this. F of x minus 1 squared is equal to x minus 1 cubed over, here I can factor x minus 1 squared, and I get 1 plus x minus 1 squared. Okay, so here I can cancel these two factors, this one and this one. And we're left with x minus 1 over 1 plus x squared minus 2x plus 1, which is x minus 1 over x squared minus 2x plus 2. Okay? But now as x goes to 0, as x goes to, I made a typo here, this is 1, x goes to 1. As x goes to 1, I get x minus 1 over x squared minus 2x plus 2, that's equal to 0 over 1. Again, I get the limit 0. And maybe you might think that we have exhausted all of our options, okay? And maybe that's true. So you'll see these are difficult limits. In a certain way, you have to have some kind of knowledge how much is the limit before you start proving, because you don't know whether you need to prove that it exists or it doesn't exist. So why don't we approach this line, this point along the line, along this line right here, and that is the line y is equal to x minus 1. Okay, so in that case, f of x minus 1 is equal to x times x minus 1 minus x minus 1 over x minus 1 squared plus x minus 1 squared. Factor x minus 1 in the numerator. I'm left with x minus 1 over 2 times x minus 1 squared. X minus 1 squared plus x minus 1 squared is x minus 1. 2 times x minus 1 squared. And now, when we cancel these, I just get 1/2. Okay? And there you go. As x approaches to 1, is equal to 1/2. Okay? So we have found a path along which, if we approach to the desired point along this path, it's going to give us different limit than the previous one. In conclusion, we say that this limit does not exist. Okay? Finding the path that will give us the positive knowledge about this limit is difficult. Okay, for example, here I want to make the numerator similar to the denominator, right? And that's not easy. So for example, if I factor here the numerator y, I get x minus 1 is similar to x minus 1 squared plus y squared. Okay? And in that case, somehow I can see that if y is equal to x minus 1, then these are going to be somewhat similar. I'll get x minus 1 times x minus 1 is going to be similar to x minus 1 squared plus x minus 1 squared, exactly what we did here. Okay? But it is not always as straightforward. Not that this was an easy problem. Okay? So let's practice more examples like this. Okay, so in this example, the denominator is 0. That means that the function is not defined at the origin. Let's start with the easy cases. So here f of x y is equal to x squared minus y over x minus y. Okay, how much is the function when I take constant y being equal to 0, right? That means that I'm approaching along the x-axis. That's x squared minus 0 divided by x, which is x. So the limit of f of x 0 as x goes to 0 is equal to the limit of x, which is equal to 0. Okay. What about f of 0y? Then I get negative y over negative y, right? Negative y over negative y, which is equal to 1. And there you go. You can conclude that this limit does not exist. Limit of f of 0y as y approaches to 0 is equal to 1, because these two values are not equal. I can conclude that the limit does not exist. Okay, the next example, x squared plus sine squared y over 2x squared plus y squared. Again, let's start with the easiest. Let's just approach, we're approaching to the origin, so I can approach along the x-axis and along the y-axis, right? Because those are the easiest one to evaluate. How much is x, and then I take y is being equal to 0, I get x squared plus sine squared of 0, that's 0, divided by 2x squared plus 0 squared. Sine of 0 is 0, so I get x squared over 2x squared, and that's simply 1/2. Now the limit of this function as x approaches to 0 is just going to be this, is going to be 1/2. Then what happens when I take x being equal to 0 and I approach the origin along the y-axis? Then I get a 0 plus sine squared of y over 2 times x squared, so 0 plus y squared. This is equal to sine squared of y over y squared. Okay, so now find the limit as y approaches to 0 of sine squared of y over y squared, and here I use the limit that I already talked about in the previous video, the one that you guys should be familiar with from Cal 1, sine of theta over theta as theta goes to 0 approaches to 1. So 1 times 1, this limit is equal to 1. And in conclusion, we say that this limit here does not exist. Why? Because we have found different limits when we approach the origin along different paths. Okay, let's see this one. A limit of x to the power of 4 plus 5 divided by y. Along, you can do the same thing. F of x, y, the function that we're talking about, is x to the power of 4 plus y over y. So f of 0y is equal to y over y, which is equal to 1, and f of x0 is equal to x to the power of 4. Well, I cannot use this. I cannot say, I cannot approach this function along the x-axis, because in the denominator I only have y, right? So this as an option is, this here is not an option. So I need to find another way to approach this point that is going to be different. So when I'm approaching from here, right, along the y-axis, right, when I take x is equal to 0, the limit is 1. I cannot take y is equal to 0. I cannot express this function as f and y being equal to 0 because it's not defined as 0. So I need to find another path. Let's, for example, take any line, okay, any line that crosses through the origin, right? So that means y is equal to any constant k, positive or negative, times x, except being different than 0. So how much is going to be f of x kx? Let's see, maybe we'll get something. That's x to the power of 4 plus kx over kx. That's equal to factor x to the power of 3 plus k over kx. Now we cancel this factor, okay? And we're left with this expression right here. X cubed plus k over k, okay? Now send x to 0, limit of f, so y is equal to kx. That means any line passing through the origin. X kx, as x approaches to 0, is equal to the limit of x cubed plus k over k. As x goes to 0, that's k over k. I get equal to 1. So no matter what line do we take here, it's always going to be 1. Of course, except y is equal to k is equal to 0, because in that case I get y is equal to 0. Okay, so this might lead us to believing that this limit here indeed is going to be 1. If you doubt, if you think that this limit is 1, then you have to prove that this limit is 1, okay? But what if I take y is equal to x to the power of 4? Okay, what if I approach the origin along this curve? Then, so this is one try, second try. Now the third try, f of x to the power of 4, that's x to the power of 4 plus, instead of y, I have x to the power of 4 over x to the power of 4. That's 2 times x to the power of 4 over x to the power of 4, and that's simply 2. So I have found a path along which, when I approach to 0, I get different limit than some other path that I used before. So from here, it implies that this limit does not exist. Okay, now we're going to use another technique that is very convenient when we're approaching towards the origin and I have as an expression x squared plus y squared. Okay, in that case it's very convenient to switch to polar coordinates. Okay, so what were the polar coordinates? X is equal to r times cosine theta, and y is equal to r times sine theta. Recall that r is always positive or equal to 0 if we're talking about the origin, right? So if I take x is equal to r cosine theta and y is equal to r sine theta, then x squared plus y squared is equal to, you should know this, r squared cosine squared theta plus r squared sine squared theta factor r squared cosine squared theta plus sine squared theta is 1. So that means that x squared plus y squared is equal to r squared. Okay? So let's see how this function is going to look like when we switch to polar coordinates, okay? So x is r cosine theta. That means that x cubed is going to be r cubed cosine cubed theta over x squared plus y squared is simply r squared. Okay, and now when we switch to polar coordinates, then r approaches to 0 from the right. Why? Because when we're in polar coordinates, we approach, the radius approaches, diminishes, shrinks to 0, right? It's always positive, that's why it goes always from the right, independently of the angle, right? So we're going towards 0, we don't care about theta, okay? The only idea is that the radius shrinks to 0. So we simplify this expression. You get the limit as r approaches to 0 from the right, r times cosine cubed of theta, and no matter how much is cosine cubed of theta, right, it can be between -1 and 1, times 0, this limit is equal to 0. Okay? So one more time, whenever we have the expression x squared plus y squared, where x and y are approaching towards the origin, it's very convenient to switch to polar coordinates. Okay, then x squared plus y squared simply becomes r, and the limit approaches to 0 from the right. Okay, so let's practice two more examples like this. In this example here, I have x squared plus y squared. I switch to polar coordinate, that means the limit as r approaches to 0 from the right. In the denominator, x squared plus y squared is r squared. You should get used to that, especially later on when we're going to do double and triple integrals. And then x squared is r squared cosine of theta. Look what happens here. Now r squared cancels. Okay, this function here doesn't depend on r, so it's being actually treated as a constant, right? So this is just equal to cosine of theta. But now, no matter how much is theta, this one doesn't converge to any particular number. For different theta, I get different value of cosine of theta, which means that this limit doesn't have one unique value. In that case, this limit simply does not exist. And in the last example, as far as I remember, again, I have x squared plus y squared. X and y are going toward 0, so this I switch right away to polar coordinates. R goes to 0 from the right. In the denominator, I have r squared. And here on the side, I'm just going to negative x squared minus y squared is negative x squared plus y squared. In polar coordinates, that's negative r squared. So the numerator is e to power negative r squared minus 1. Okay, as r goes to 0, the numerator is e to power 0 is 1. 1 minus 1 is 0. The denominator is also 0. So what can we do? We can use the L'Hopital's rule. This limit as r goes to 0 from the right. Derivative of 1 is 0. So e to power negative r squared. Derivative of e to power u is e to power u times u prime. That means derivative of e to power negative r squared is e to power negative r squared times the derivative of negative r squared, which is negative 2r, divided by the L'Hopital's rule, derivative of the denominator, which is 2r. And then we cancel these two expressions, send r to 0, e to power 0 is 1, times this negative, the answer is negative 1. And the last example that we're going to say, the last limit we're going to solve by using polar coordinates. This is equal to the limit, as r approaches to 0 from the right, cosine of, so x cubed minus y cubed is going to be r cubed cosine cubed of theta minus r cubed sine cubed of theta over r squared, right? X squared plus y squared is r squared. We already talked about this. Now I can simplify this expression here. Okay. And I get cosine of 1 factor of r times cosine cubed of theta minus sine cubed of theta. Okay. Now send r to 0. That means that this whole expression is going to go to 0. So this just simply becomes approaches to cosine of 0, and cosine of 0, as we all know, is 1. And the last notion in this section is going to be the idea of continuity. And we say that a function defined in two variables f of x, y is continuous at the point x naught, y naught if f of x naught, y naught is equal to the limit of the function as x, y approaches to x naught, y naught. And this here is the definition of continuity at the point, but if we think about what it says, then we are talking about two conditions. First of all, that this here exists, that is defined, or in other words, that the point with coordinates x naught, y naught is in the domain of f, and that's the first part. F is defined as at x naught, y naught, or in other words, f of x naught, y naught exists, or in other words, x naught, y naught is in the domain of f. And the second part is that this limit here exists. Okay? So if any of these three cases are not satisfied, then we say that the function is not continuous at the point x naught, y naught. And let's do an example. It says, show that the function defined as 2xy divided by x squared plus y squared for all the values except the origin, and xy being 0, sorry, f of xy being 0 at the origin, right? Show that it's continuous at every point except the origin. Okay, so first of all, let's look at the points outside of the origin. They're defined. The function is defined at any other point. Why? Because the denominator stays away from 0 for any point besides the origin. Okay, so whenever xy is not 0, 0, then this function is defined. I can evaluate it, and it's continuous there. So that means that the limit exists. So we're done. The question becomes, what happens to the function at the origin, which means we have to show that one of these three conditions are going to fail. Well, is the function defined at 0, 0? Yes, by definition, f of 0, 0 is equal to 0, right? So the origin is in the domain of this function. Now let us check now whether the limit of f of x, y exists as we approach towards the origin. If it does, then that limit has to be equal to 0. But we are basically, there is a hint in the question says that it's not continuous at the origin. So basically, we have to fail somewhere. Either this function is not, this limit does not exist, or if the limit exists, then it's not equal to 0. So let's say this is the limit of 2xy over x squared plus y squared as x goes to 0 and y goes to 0, okay? So right away, if I approach the origin by the point x is equal to y, okay, so f of x, that's equal to 2x times x over x squared plus, now y is x, so x squared, so 2x squared over 2x squared, that's equal to 1. Okay. On the other hand, if I approach along the x-axis, so x0, right, I get 2x times 0 over x squared plus 0 squared, which is 0 over x squared, which is equal to 0. So the limit does not exist, which implies that the function is not continuous at the origin.